So starting chapter 17 is on reaction kinetics. This is basically looking at how reactions actually take place and activation energy and rates of reaction, things like that. So the first section is just on the reaction process. Oh, okay, of course, now people show up. Hold on. All right. So by studying many types of experiments, chemists have found that chemical reactions occur at wildly differing rates. For example, in the presence of air, iron rusts very slowly, whereas methane in natural gas burns rapidly. The speed of a chemical reaction depends on the energy pathway that a reaction follows and the changes that take place on the molecular level when substances interact. In this chapter, you will study the factors that affect how fast chemical reactions take place. A lot of this will probably be common sense. For example, if you increase temperature, you will increase the reaction rate, things like that. We're going to talk about that in a later section. But looking at how a reaction actually occurs. If you mix solutions of hydrochloric acid and sodium hydroxide, a quick neutralization reaction happens. This is the overall ionic equation. Remembering that an overall ionic equation shows you the spectator ions as well. So if we have HCl, a better representation of hydrochloric acid is hydronium ion plus chloride ion. And of course, sodium hydroxide is represented by sodium and hydroxide ions in solution. When they react, the hydronium will combine with the hydroxide to form two water molecules, and the spectator ions you're left with are sodium and chloride. Just a second, Emily's here. All right. Now, this reaction is nearly instantaneous. The reaction is only limited by the speed at which hydronium and hydroxide can diffuse through the water to meet each other. Reactions between ions of the same charge and between molecules are not immediate, however. Positive and negative ions will repel each other. I don't mean that positive repels negative. I mean positive and positive repel each other, negative and negative repel each other. You also have electron clouds of molecules that repel each other at short distances. So only ions or molecules that have very high kinetic energy can overcome the repulsive forces enough to react. Another example is colorless hydrogen gas is made of pairs of hydrogen atoms bonded together as diatomic molecules. Remember, there are 7 diatomic elements: hydrogen, nitrogen, oxygen, and the 4 halogens: fluorine, chlorine, bromine, and iodine. Iodine vapor is also diatomic and it is purple. The chemical reaction between these two at a high temperature makes hydrogen iodide, HI, which is a colorless gas. Now, this reaction is reversible, and the hydrogen iodide molecules will decompose and reform hydrogen and iodine gas. Now, these two equations only show which molecular species disappear as a result of the reactions and which species are made, but it doesn't actually show you what's called the reaction mechanism, which is the step-by-step sequence of reactions by which the overall chemical change occurs. It only gives you an idea of the overall reaction. It doesn't actually tell you how the molecules actually interact with each other to form these products. Experiments can be designed that suggests a most likely step or steps in reaction mechanism. Each step is going to be very simple, and the equation for each step represents the actual atoms, ions, or molecules that participate. A lot like how when we go from an overall ionic equation to a net ionic equation, the net ionic equation only shows you the ions that are actually participating in the reaction, but the overall ionic equation actually tells you what's really represented in the solutions. Now, it was thought that the formation of hydrogen iodide was a simple one-step process. It involves two molecules, H2 and I2, in a forward reaction and two HI molecules in the reverse reaction. But experiments showed that there's never a direct interaction between H2 and I2. So the original thought of the reaction mechanism for this reaction is not correct. And the only way that we can determine, by the way, the only way you can determine reaction mechanism is through experiments. Now, there are two alternative reaction mechanisms for this overall equation. You add up the steps in each reaction to give your overall equation. Now, you're going to end up having some molecules that exist in the steps which do not appear in the overall equation. These are called intermediates. So these are kind of in between molecules that are formed during the reaction process, but they don't occur in the overall final reaction. So the two possible mechanisms for the formation of hydrogen iodide. The first mechanism is a two-step process. In the first process, diatomic iodine splits into two individual iodine atoms. Then these two iodine atoms are going to react with H2 to form two hydrogen iodide. Now, in this example, the individual iodine atoms are the intermediates. They cancel out. There's two on each side, and you get your overall equation anyway. But this is one possibility. Again, experimentation shows that this I2 and H2 never directly interact with each other. The second possibility is a three-step process. The step one is the same. Diatomic iodine dissociates into two individual iodine atoms. In the second reaction mechanism, step two includes an intermediate where you have an individual iodine atom reacting with diatomic hydrogen to form H2I, and then H2I interacts with the second individual iodine atom to form 2HI. Again, in this mechanism, both the individual iodine atom and the H2I are the intermediates. You can see how there's 2I on the side, 1, 2 on the left, so they cancel, and there's one H2I on each side. So they do not appear in the overall equation. These are what are called reaction mechanisms. The truth is we don't really know which one of the two it is, but we do know that it's one of these two possibilities. That was an example of what we call a homogeneous reaction. This is where the reactants and products are all in one phase. In that example, they were all in the gaseous phase. Now, it might sound kind of stupid to say that for a reaction to occur, the atoms or molecules must collide. I think we all kind of figured that. Like, you can't have any kind of rearrangement of bonds if atoms or molecules don't hit each other. But there's two very specific criteria that are required in order for a successful reaction to occur. The collision has to result in an interaction between the particles. What that means is that you can have two molecules or atoms. I'll just use the word molecules to refer to everything. You can have two molecules hit each other, but they don't react. So hitting each other is not enough for a reaction to actually occur, because if they hit each other, they might not hit each other with enough force to actually make them interact with each other. They might repel each other from the electron clouds, and then they just kind of bounce off each other, kind of like if you ever play pool or snooker. When one pool ball hits another one, they just hit each other and bounce off. So collision theory is a set of assumptions regarding collisions and reactions. And it's a lot easier than the kinetic molecular theory, which is how we started off this year, talking about the 5 assumptions of an ideal gas. Collision theory, there's only 2 requirements. So let's consider what happens on a molecular scale in one step of a homogeneous reaction system. Hold on one second. Okay. All right, so we're going to look at, and it's very unfortunate that we are all at home because I have a great set of a molecular set at school, which I use to help visualize this process. But well, there's not much I can do about that. So if I have a reaction system, so I've got AB plus AB yields A2 plus 2B. According to collision theory, let me change that, collision theory, not collisions theory. In order for a reaction to occur, these 2 AB molecules have to collide. That's rule number 1. If they don't collide, nothing's going to happen. But here's the 2 criteria for collision theory. They also must collide, number 1, in the right position, and number 2, with enough energy to combine their valence electrons and disturb the bonds. These are your 2 criteria under collision theory for a successful reaction: the right position with enough energy, 1 and 2. If they don't collide with enough energy, as I said, you're not going to disturb the bonds. Most likely the repulsion from the electron clouds will just repel the 2 atoms or the 2 molecules away from each other, so they'll hit and bounce off. If they are not in the right position, for example, let's just do this. Here's A, and here's B. Okay? If they collide in this position where B hits A, that is not a possibility over here. You either have 2 individual B atoms or you've got A2. But if they hit in this arrangement where this B hits that A, nothing is going to happen. I don't have any way to rearrange because I'm using Keynote, but okay. Let's say I've got, here's A, B, and A, B. Now, if these 2 hit in this arrangement, because A is the red one, B is the yellow one, if they hit in this orientation, it is possible that a reaction will take place because one of the possible products is A2. So if these 2 molecules hit each other in this position, they're in the right orientation or the right position to create one of the products. And the second criteria is that they have to hit with enough energy to disturb the bonds. So if they're very slow, or if they don't have enough kinetic energy, even the 2 A's hitting each other will just kind of gently hit each other and bounce off. They have to hit with enough energy. So it's not just enough to collide. It's not enough to collide in the correct position, but it has to be you collide in the right position with enough energy. That's collision theory. If they do collide in the correct position and with enough energy, then it will result in a chemical reaction. So for part A, the collision is too gentle. So we've got AB, AB. They're in the right position because you see the 2 A atoms collide with each other. But if they don't have enough energy, they're just going to hit each other and bounce off. In this example, the 2 B atoms are hitting each other. That's not even a remote possibility for a product. So it's not in the correct orientation. It's only if it's in the correct orientation with enough energy that you actually create one of the products. And here you've got the individual B atoms left over. Okay, if they're not in the right position, they rebound without interacting. But an effective collision, again, 2 criteria: right position, enough energy. The most important thing to remember is not every collision creates a reaction. Okay, and then of course you throw into the mix, if you have ions, then you've got the repulsion of like charged ions, positive repels positive, negative repels negative. So going back to that first example that I had of hydrochloric acid with sodium hydroxide, forming 2 water molecules plus sodium and chloride. Now, again, think about what this means. This means you've got hydronium. I'm not going to draw everything, it'll take too long. And chloride, sodium, and hydroxide. So these are the 4 that have to mix. Now imagine the key to a successful reaction is forming the water. The sodium and the chloride have nothing to do with it because they're spectator ions, but they do play a huge part in getting in the way of these 2 ions that have to react with each other, right? In the very beginning of the lesson, I said the only thing that limits the speed of this reaction is the rate at which the hydronium and the hydroxide can actually get together. So the hydroxide has to go through a sea of also negative chloride. Hydronium also has to try to avoid sodium. So that's the only thing that's limiting that reaction. Okay, so unless the collision brings the correct atoms close together in the proper orientation, molecules are not going to react. Let's take a look at another example. If chlorine collides with oxygen at the end of nitrogen monoxide, the following reaction may occur. So the chlorine, the chlorine bonds to the oxygen. So this chlorine molecule has to come into contact with the oxygen molecule. If it comes into contact with the nitrogen, not the oxygen molecule, sorry, the oxygen atom, if the chlorine hits the nitrogen side of NO, then nothing's going to happen. Okay, because oxygen is the atom that the chlorine can bond to. All right, I think the last topic, it didn't take as long as I thought. Activation energy. I know I have mentioned this in biology, but just to talk about it again, hopefully you understand that activation energy, especially when I was drawing the energy diagrams before, if you've got exothermic, your products have less energy than your reactants. And so, well, that's kind of small, but anyway, the difference in energy between your reactants and your products, that's delta H, right? And endothermic, the reactants have less energy than the products. Again, delta H. Sorry, that's so tiny. Maybe it's not as tiny as your screen is on my iPad. Anyway, so the difference between, let's do blue, your reactants and the peak of that's your activation energy. And I always use the metaphor of, or the analogy, I don't know, I guess it's like pushing up a ball up the hill. So the analogy of pushing a ball up the hill, it requires energy from you to get the ball to the top of that hill. But once you're at the top, all you need to do is just get it a little push, and you don't need to add any more energy. Activation energy works the same way. So let's look at the formation of water. So you've got 2 moles of hydrogen gas that react with 1 mole of oxygen gas to form 2 moles of water. The heat of formation is negative 285.8 kilojoules per mole. So I should actually, not a half, H2 plus a half NO2, H2O, and that's exothermic. So that would be written like that. If you wrote with the enthalpy included in the reaction, exothermic, so it belongs on the right-hand side as a product. The free energy change is also very large. We just finished doing free energy delta G, negative 237. So anything that's negative, wait, where did my mouse go? Anything, any value of delta G that is negative means the reaction is spontaneous. So this will absolutely be spontaneous. But the question remains, if I take a canister of hydrogen gas and a canister of oxygen gas, and I mix the two gases, they don't spontaneously turn into water. So why is that? There's literally hydrogen gas and oxygen gas in the atmosphere. It doesn't magically just react with each other, even though delta G is so negative. This is an incredibly negative value for free energy, which should mean the reaction occurs just like think, as soon as hydrogen and oxygen come into contact, it makes water. Why doesn't that happen? Well, on the molecular level, when diatomic hydrogen and oxygen approach each other, the electron clouds repel each other. So the molecules bounce off each other and never actually meet. In order for an actual reaction to happen, the molecules, this is requirement number 2 for collision theory, the molecules have to have enough kinetic energy to actually disturb the valence electrons. This is because you have to break the bonds in the molecules of your reactants in order for them to form new bonds. Bond breaking is always endothermic. It always requires energy to break the bond. So whatever the heat of formation, or whatever the energy that it takes, no, sorry, let me try that again. The energy that is released when hydrogen is formed is the energy you have to put into hydrogen in order to break those bonds. Forming new bonds is always exothermic. The initial input of energy needed to overcome the repulsion is the initial energy that activates the reaction, hence activation energy. Now, because you're starting with brand new or like undisturbed molecules, you need that initial input of energy to activate the reaction. Once you actually break those first bonds, when the new bonds formed, they release energy, and this is enough to keep the next ones going. This is enough energy to break the bonds of more hydrogen and oxygen and keep the reaction going. I just said that. So once the activation energy is reached, the reaction rate will increase. It's only limited by the time required for the reactant particles to get the energy and make contact. Okay, but it's just that first initial energy that's required. So activation energy is abbreviated EA, and it's the minimum energy required to transform the reactants into an activated complex. Now, what's an activated complex? Hold on a second. Well, I'll come back to that. Okay, an activated complex is something that's in between the reactants and products. If you go back to when I talked about intermediates here. Oh, the iPad doesn't like that. Nobody likes that. I'm frozen. Oh, here we go. Batman. Where are my reaction mechanisms? Here we go. So any of the intermediates, these would be considered activated complex, somewhere in the middle, like you're in the middle of breaking the old bonds and forming the new bonds. That's the activated complex. Oh, now I gotta go all the way back. I think it's here. Nope, is it there? There we go. Okay. So if the forward reaction is exothermic, then the reverse reaction is endothermic, because the water molecules in the example of the formation of water, the water molecules are at a lower energy level than hydrogen and oxygen. So if we were to look at, again, H2 plus O2 yields H2O, that's a half, or we got 285.8, something like that. So because it's exothermic, that means that the reactants have more energy than the products. So if you try to go in reverse, it's going to be H2O plus 285.8 yields H2 plus half and O2. This is endothermic. Okay, just like in Hess's law, I told you, if you reverse the equation, you have to reverse the sign of delta H. This is a reflection of that, because if one direction is exothermic, the opposite direction has to be endothermic. So looking at, okay, that's fine. So depending on which direction you're going, the activation energy might be greater. So this, from here to here, that's activation energy. But from here to here, that is EA prime. That's the activation energy for the reverse reaction. You can see that the activation energy for the reverse reaction is much greater because it's endothermic. Okay, endothermic reactions are going to have a much higher activation energy than exothermic reactions. Oh, okay, so I just had it all here. Great. Right, so forward reaction, which is exothermic, shown by the fact that the reactants have more energy than the products. So this actually is also not, it's not delta E, delta H. I prefer delta H because we've already studied enthalpy. The reverse reaction is endothermic. So you've got EA prime going from the products up to the energy of the activated complex. The activated complex is going to have the greatest potential energy. So again, once you get that ball up the hill and then whoop, it'll go by itself. Okay. So as I said, the activated complex is kind of an in-between where bonds are partially broken and new bonds are partially forming. That's called the activated complex. Just that in between. It's always the peak of the activation energy curve, I guess. Both forward and reverse reactions. Oh, wait, that was a video. Hold on. Yeah. Okay. So the activated complex in this reaction appears green. So it's some kind of weird in between the reactants and products. Okay, screw the music. He's not explaining anything. But you can see from this reaction that reactions are not always instantaneous, right? Sometimes it takes time. And part of the second half of this chapter is talking about reaction rate and what affects reaction rate. In this example, it's activation energy plus the collision theory being A and the A2 plus B2 forming this activated complex. And now obviously we see more of the completion of the reaction. Okay, where do you go with this? Still the music. So here's your products, AB plus AB, 2AB. Products, yeah, I get it, buddy. Okay, pink again. Yeah, great. All right, let's look at the energy diagram then. It would have been nice. I know he has a thermometer in there. It would have been nice if he or she, I don't know if this is a man or woman. Okay, I don't care about the music. It would have been nice if, because they had a thermometer in the beaker, they would have actually shown any temperature change, because according to this, it's exothermic because the reactants have a slightly higher energy profile than the products, but well, I guess I can't complain unless I just go make my own videos, I suppose. All right, so obviously, because the forward and reverse reactions are both part of the same system, they're going to go through the same activated complex. The bond that's broken in the activated complex for the forward reaction must be reformed for the reverse reaction. Remember that the speeds, therefore the kinetic energies of molecules, increases as temperature increases. So if you increase the temperature, you increase the speed of the molecules, which increases the number of collisions, which is going to result in a number of increase of successful collisions. Okay, but even if you increase collisions, you still need to have enough kinetic energy when they collide and the correct orientation. You are increasing the likelihood that they're going to collide and collide with enough energy. So increasing the temperature increases the possibility of a successful collision. The activated complex, as I said, is kind of a mixture between the reactants and products. Now, once the activated, if you could freeze the reaction when the activated complex is formed, some activated complex will go in reverse. Kind of like if you get the ball to the very top of the hill, you have a 50-50 chance whether it will roll backwards or roll forwards. And that's why I really love using the ball on the hill analogy, as you might have noticed. So it's not guaranteed that the activated complex will actually complete the transformation into the products. So it's kind of a 50-50, either are just as likely.